Yeah, I forgot to hit record, but yes, I got the early morning session too. Go ahead. I'm sorry, I missed that part. You said 0 point.
1 minus 8090.8090 is 1.191.
0.190.
0.191.
191. Okay, good. So 80.9% for that. And then if we multiply this by 100, that's going to be 19.1% for the boron 10 isotope. Right. So what we have is we calculated our fractions based on X and 1 minus X because we had two isotopes that we were dealing with. All right. So once we this is another tool that we have, right? Normally we'll either have all the fractions and all the isotope masses and have to figure out the average atomic mass. But we also had, in this case, we had the average and we had uh, no fractions, but we could solve for the fractions by making one of them X and one of them 1 minus X. All right. So we're going to do one more. Dealing with this average atomic mass, and then we're going to move into another topic. So we have another problem here. And well, before we do that, are there any questions about this um, second part of this problem? Again, I didn't hit record at the very beginning when I was copying and pasting, but the only number for the second part of the problem, the only number that changes is this number. Because the average atomic mass for the United States was 10.819. Everything else stays the same. So that's why we were able to just use the same numbers from the previous set of calculations. All right. Any questions about that part of the example? All right, let's go and do another one. This one is kind of tricky, but we're going to work through it, and then you'll have another set of tools in your toolbox to solve these types of problems. Can somebody read this problem for me? All right, anybody? I know it's Friday.
I'll do it.
Hmm?
Magnesium has three naturally occurring isotopes with atomic masses of 24 point and 25 point AMU respectively. If the average atomic mass of magnesium is 24 AMU and 78.99% of all magnesium is 24 mg, what are the abundances of 25 mg and 26 mg?
Okay, so all of that is all, we have all this information. Now let's think about what this problem has already given us. So we have all three isotope masses. All right, we got all three isotope masses. We have the average atomic mass. And then we got another piece of information because it told us that for magnesium 24, that 78% of all of these isotopes that exist is magnesium 24. So we even have the fraction right, for magnesium 24, which is, it said 78.99%. but we can convert that to the fraction by just dividing by 100. So it's 0.7899. So this is the fractional abundance for magnesium 24. All right. So we have a lot of information to work with. What don't we have? Because this is what we have to solve for. We need the fractions for magnesium 25 and magnesium 26. All right. So how are we going to do that? It gives us a huge clue by telling us the percentage of magnesium 24. It says that the percentage is 78.99%. So if the total percentage of all isotopes has to add up to 100, what's left over from 100 if mag 24 takes up 78.99% of that 100? Because this is the key to the problem. Let me ask it this way. How much, what's left? So those two fractions that are left, what would they have to equal? Let's think about it. If everything has to add to 100% and you subtract that from that 78.99%, what's left of that? Just remember, everything has to add to, all the fractions have to add up to 1. All the percentages have to add up to 100. So 78.99%. So what am I left with? Is that right?
Yep.
21.01%. So those other fractions have to add up to 21.01. So that's what this means. Right, so 0.2101. That's what that 21% means. Was the other two isotopes that are left, their fractions have to equal 0.2101. So the way we're gonna, this is the key to the problem. The way we're gonna solve this is we're gonna make one fraction x. What will we make the other fraction? Anybody, what will we make that second fraction? If one is x, and we know the total that the two have to add to, what would the second fraction be? Is that right? Wouldn't it be the total minus x to give me the second fraction?
Yes, sir.
Yeah, it's just like the other problem. The only difference is they gave us one fraction. And so we have an amount that's left from that fraction. And both of those two, the second and the third fractions have to equal up to that amount. So if we make one x, the other one is going to be 0.2101 minus x. All right. I saw that too. I see it now. Anye, the amount 21.01. I appreciate that. And I see your answer too, Mary. So now we can set this up because now we know the average atomic mass. We know that equation, right? We know that it is equal to the sum of the fractional abundance times the isotope mass, whatever the isotope is. Let me ask this question. How many terms is this sum going to have for this problem? If there, okay, I see a chat pop up. Okay, you're close, Mary. The sum is going to have three terms because you have three isotopes. Remember, this piece right here, this is for every isotope. So if I have three isotopes, I'm going to have three of these terms that make up that sum. All right. So now we know that, and we know how we're going to set this up with X and 0.2101 minus X. Now we can go in and solve this problem. So we know the average atomic mass that was given, which is here, 24.3050. So I'm going to use that. And I'm going to put that here. And I'm going to set that equal to 0.7899 times the magnesium 24 mass, which is 23.985042. All right, that's one. So this is again the fractional abundance, and this is the isotope mass. And then I'm going to do that two more times for the other two fractions. So it's going to be plus. Now, what I want to do with the X and the 0.2101 minus X, I want to make the X term, I want to give that term to the number that's closest to the average mass. All right, so we're going to do that by taking that magnesium 25, which is 24.985837. And then we're going to make that times X. Are we following? So this is, we want to make the X term using the isotope mass closest to magnesium 24. So the isotope that's closest in mass to the average atomic mass, that's what we're going to use for X. All right. And then the other term, the third term, because this is a sum, is going to be for magnesium 26. So this is 25.982593. And then this is going to be times 0.2101 minus X. Any questions so far? So we set it up the same way. It's just that our fractions, our X terms are a little bit different. All right, so this number we can just bring down, because that times X is just going to be 24.985837X. And then the back term we need to distribute. So this is going to be times that and times that. So that's going to be minus 25.982593X plus, can somebody calculate that number? 28.982593 times 0.2101. And while somebody's calculating that, I need somebody to calculate this number right here. 0.7899 times 23.985042. All right, anybody got either one yet? Okay, thank you, Mary. I agree with that. I'm going to take it to 4 sig figs. So we're going to say 18.9, actually 5, 4, 6. Actually, let's take it to 6 sig figs. 9, 4, 5, 8. Excellent. What about the second one? And this is plus because this is a sum. What about the other number? Okay, thank you, Brooklyn. 5.459. Good. Let me put that in pink. We can keep up with everything. These problems are, this is a long drawn out calculation. Good. Excellent. Now we can combine like terms. So we can combine these two. I'm going to highlight them because these are numerical terms. And then we're going to combine these two. Let me pick a different color. These two, this term right here and this term right here, because these are X terms. All right. So 18.9458 plus 5.459. We're going to combine that, and that's going to combine to 24.407. I'm sorry, 4047. All right. And that's going to be plus minus, I'm sorry, 0.996756X. And all of this is equal to the average atomic mass, which is 24.3050. And again, this is magnesium 24. What I color coded with up here. 24, I think, was yellow. So that's magnesium 24. And then 25 was orange. Just trying to make sure we can keep track of all this stuff. So this is orange. This is magnesium 25. And what do I have for 26? Green. So this is magnesium 26. All right. So now we can just, we want to get the X term by itself. So we can subtract 24.4047 from both sides. All right, can somebody give me that number? And this is equal to 0.996756X. All right, again, once we solve for X, we're home free because we can go back and plug it into the 0.2101 minus X to get the second fraction. X is going to give us the fraction for magnesium 25. All right. Anybody got it? It should come up to be a negative number. Okay, thank you, Mary. Negative 0.0997. Good. So now we can, again, we can solve for x. So we're going to divide both sides by 0.996756. That's going to cancel these terms out. And then this is negative 0.996756. Can we get that real quick? The negative signs are going to cancel. So this is whatever this number is going to be equal to x. Should be somewhere around 0.1 or something like that. Okay. I'm just going to say 10002. We'll leave it right there. All right, so now we know what x is. Thank you, Mary. We know what x is. X is 0.0012. This is the fraction for 25, magnesium 25, which I think was orange, right? So now we can turn that fraction into a percentage by taking it and multiplying it by 100. And it's going to equal out to about 10.002%, which we can just leave at 10%. All right, now what do we need to do to find the other fraction? Because this is the x term, and we have another term for magnesium 26, is that right? That's in green. Right, let's go back up here. What was the term for that fraction? You see it, 0.2101 minus x. So once we find x, we're going to go back and plug it right into that. So the fraction for MG26 is 0.2101 minus 0.10002, which gives me what? Right, remember this is x that we solved for. So we solve for that and we just plug it right back into that other term. Okay, 0. I see it. Thanks, Mary. 0.11008. That's the term for that. The fraction for the second term. And if we multiply that by 100, that's going to give us the percentage. So it's going to be 11.01% because we can round that up. All right, any questions about that? I know it's kind of a in the weeds problem, but once we figure out what we're looking for and we know how to set that equation up, then it's just it's all academic after that. So mag 25 is 10% and mag 26 is 11%, and the total should give us 100. So if we add 78.99, 11.01, and 10%, we should get 100%. All right. Any questions about that? Feel free to unmute. Take a deep breath, a sigh of relief, all of that. All right. So this will all be posted to Blackboard after class too. Let's go to the next section because we've done average atomic mass. We've done calculations of protons, neutrons, and electrons. We did that Thursday. We did it Wednesday as well. Let's go to the next section. And now we're going to start this section on chemical nomenclature. I can get my writing together. And this is a big word, nomenclature. All it means is naming. That's all we're going to be doing is naming. And there are some other concepts that fall under nomenclature. And two of those concepts are illustrated in this problem right here, where we have, it's asking us to write the molecular formula and the empirical formula. So the molecular formula is all the symbols and subscripts, right? And with the symbols and subscripts, the subscripts tell me how many of each atom is present. Right? So when we write out a molecular formula, we write it out using the symbols, and we use subscripts to tell us how many atoms are present in that formula. So in this particular formula, what do we have? We have a carbon, is that right? And then we also have 2 oxygens. So when I write the molecular formula for that, I write it not like that. I write it like this: carbon and then oxygen. But the fact that there are 2 oxygens here in this molecule, I have to indicate that with a subscript. So that subscript is always going to tell me how many of each atom is present. Right? If I write for this one, I cannot write an empirical formula. And I'll tell you why. Empirical formulas, this is basically the reduced version of a molecular formula. So it's the reduced version of the molecular formula. So it is basically taking the lowest common denominator of the subscripts. In this case, the carbon is understood to be 1, but we don't show that. Anytime it's 1, we just leave it. It's understood to be 1. And if we divide by 1, everything is going to stay the same. So we can't break this down any further. Right, so can't break that down any further, so we leave it as it is. All right, let's go to B. Let's go to B. B, I'm gonna erase this 1, 2, because we don't need it. I don't want you to get in the habit of doing that. B, how many carbons do we have?
2.
2 carbons, all right. How many hydrogens?
2.
2 hydrogens, right? So the molecular formula for this compound, I'm gonna sneak you another piece of information too in a second. But the molecular formula for this is C2H2. That's my molecular formula. The empirical formula is the reduced version of their molecular formula. So both of these are 2s, and I can divide everything by 2 and end up with CH, which is the empirical formula, right? It's the reduced version of the molecular formula. So it's down to the lowest common denominator. So both of those 2s, if I divide everything by 2, I end up with 1 carbon and 1 hydrogen. So it's just CH. All right. This compound itself, what kind of bond is this? Anybody remember when we talked about this? It was a while back, couple of weeks ago.
Triple
Speak up.
triple bond.
Triple bond. Good. It is. You know, today is the International Women in Science Day. So speak up. You're a woman in science. So we got a triple bond. This compound belongs to a class of compounds in organic chemistry called alkynes, N-E-S, Y-N-E-S. And it's the Y-N-E-S, that suffix tells me that there's a triple bond present. So this is what we call a suffix. It's on the end of the name, and it indicates a triple bond, not a triple bond. All right. This compound itself is called, it's a compound called acetylene. It's actually used in blowtorches as a fuel for blowtorches. But the molecular formula is C2H2, and the empirical formula is CH. All right, let's do the next one. What type of bond is this between these 2 carbons? And is it covalent or ionic? That's another piece of information that I can slide in. Even
what's
though
the
we got
other bond? I ain't heard about that one.
right here? All right,
I know it's a double bond, but you said covalent or something else. I ain't never heard of the other one.
ionic. Yeah, we can talk about that now. So this is a covalent bond. It's also a double bond. Right? So covalent bonds you get from sharing of electrons. Ionic bonds will be something like this: sodium, this is plus, chlorine minus. I'm gonna put some electrons around it. Right, so this is what we would call an ionic. It's not even really a bond because there's no shared electrons. It's an ionic attraction. So the positive sodium is attracted to the negative chlorine and vice versa. So you get what is typically called in the textbook an ionic bond, but it's really not a bond. A bond only happens when you share electrons. So it's more of an attraction. So any bond between metal and non-metal is going to be ionic. Not any, 99%, because there are some exceptions. So 99% of the time, a metal, non-metal bond is going to be considered ionic. And then by the same token, bonds between 2 non-metals are usually covalent. I'll write that over here. Now those non-metal bonds can be polarized to the point where they are close to being ionic, but it's rare. It's really rare. All right, so that's a double bond. This is in organic chemistry. This is a class of compounds that we call alkenes. Notice the enes, just like ions for triple bonds. So this suffix means that there's a double bond. All right. Let's talk about the molecular formula right quick, and then we're gonna come back and talk about the what this particular alkene is used for. So how many carbons do we have?
Two.
2 carbons. How many hydrogens?
4.
4. Good. 1 here is covered up here, here, and here. So C2H4. That's the molecular formula for that compound. All right. We can write the empirical formula by reducing it down. So if we divide everything by 2, we end up with CH2, which is the empirical formula. So how many of you have ever heard of ethylene? Anybody? That's what this compound is. So ethylene is like it's a gas, but it can also be turned into a polymer. It's a monomer by itself, but if you shine UV light on it, you can polymerize it. And so if you make it ethylene into a polymer, you get what's called polyethylene. There's a bunch of different uses for that. Your cell phone case is probably some polymer, polyethylene derivative. Any plastic, if you got a plastic trash can in your room, plastic containers, all of those are polyethylene derivatives. And then there's high density polyethylene, so that's hard type plastics. And then low density polyethylene, which is like wraps, plastic wraps and things like that. But yeah, this is a very important compound. And I told the class this morning, I tried to make polyethylene from apples, because when apples decay, they give off ethylene. So my son and I, we did this science project where we tried to trap it. We had a UV light inside a mason jar with the apple, trying to trap and catch the polyethylene and polymerize it. But I think our UV light was the wrong wavelength because it didn't work. All right, let's do this last one and then we'll stop and we'll pick up on Monday. So here, this is this compound itself is an acid. So somebody asked this morning, like, why did I lead with the hydrogens? If it's an acid, then we lead with the hydrogens. So how many hydrogens do we have? It's an IUPAC convention.
2.
2 hydrogens. What about sulfurs? How many sulfurs?
1.
1 sulfur, and then you can see that 4 oxygens. Right, this is another one that you can't break down. So this is the molecular formula, but we can't take this any further, right? If we divide by 2, we'll have a fraction for sulfur. And our subscripts can't be fractions, they have to be whole numbers. Going all the way back to the law of constant proportions and the law of multiple proportions, that when you make compounds, the atoms combine in small whole number ratios, not fractions. So we have no empirical formula here. All right, any questions about anything? All right, if not, we're gonna stop here and I'll post this recording